Here's a model we've looked at several times already in this course, a model for monthly average temperatures in Cambridge. We know by now very well how to estimate the parameters in a model like this. For example, we can estimate the gamma term, the annual rate of temperature increase. For this data set here, just the temperatures from 2010 to today, the estimate for gamma comes out to be 0.05 degrees centigrade per year, which is rather scary. But just an estimate without any context is worthless. The data is noisy, so my estimate is unreliable, and if I can't tell you how unreliable it is, then you should feel free to ignore what I tell you. So, the question we have to ask is this: how confident should I be in my estimate? This question is at the heart of any piece of science, and Bayesians have a way of answering it. They say we should represent any unknown parameter by a random variable and learn its distribution given the data. Here, I've updated the plot to show the prediction uncertainty. I've taken these random variables for the parameters, I've sampled values from them, and for each random sample, I've plotted the temperatures we'd expect for those particular parameters. The parameter variables are random, so each time I sample from them, I get different values, so I get a whole load of prediction lines. And as you'd expect, the predictions get more and more variable as we project out to the future. Just a little bit of uncertainty in gamma, in other words, just a little spread of gamma values, and the further we project into the future, the bigger a difference it'll make. Here's another way we could show the uncertainty. Here I'm plotting a histogram of values for gamma. We might be lucky. It might be that gamma equals 0, but from this plot it looks rather unlikely, and it's pretty safe to say that gamma is somewhere in the range 2 to 8 degrees C per century. By the way, if you read the news, you might be surprised that my distribution here is so wide. Isn't there general scientific consensus about global warming, and isn't it much tighter than my histogram here shows? Yeah, there is. For this video, I wanted to show an interesting distribution here, so I restricted myself to just Cambridge and just the years 2010 to today. This is how much uncertainty there is about global warming on the back of just 11 years of data from one location. And even this paltry amount of data is enough to persuade me it's pretty likely there is global warming of between 2 and 8 degrees centigrade per century. So just think how much more certain we'd be if we had used all the data. Now, the heart of this method is this step here. The idea that we should represent any unknown parameters using random variables. This is the great big idea that gives us the ability to talk about uncertainty about parameters. It's the core idea in Bayesianism. The next question, of course, is how we learn those random variable distributions from the dataset. That's what this video is all about. By the end of it, we'll have seen all the steps we need to actually produce those climate uncertainty plots. So, let's start. Here's the basic idea behind Bayesian calculation. We start with a prior distribution for those random variables, that is, a distribution that reflects our belief prior to having seen any data. Then we see the data, and based on the data we update our beliefs to get what's called the posterior distribution. And the way we update our beliefs is using conditional probability. Our posterior distribution for the random variable is what we get by taking the prior random variable and conditioning on the observed data. In this video, we're going to talk through the detailed steps for doing this conditioning. We've seen all the mechanics before in earlier videos about Bayes' rule, but it's worth going through them again, partly to get used to the language that Bayesians use, but mainly to remind ourselves that we have two different ways of applying Bayes' rule, mathematical and computational, and to put the two side by side on the same problems. Okay, let's state more formally what the Bayesian approach is. The starting point for any machine learning exercise at all has to be a probability model for the observed data, the sorts of probability models we've been working with throughout this course. If we observe data little x, we'll imagine that there's a random variable big X and that little x is a sample from it, and we'll propose a probability model for big X. For Bayes calculations, we need to write this probability model out as a likelihood function, the likelihood for big X of seeing value little x. And suppose our probability model has an unknown parameter, let's call it theta. The Bayesian philosophy is that any unknown should be represented by a random variable. So I'm writing our probability model as the likelihood of x conditional on the unknown parameter big theta taking value little theta. Step 1. We have to declare our prior distribution for theta. We can set it out as a likelihood function, the likelihood for big theta of value little theta. This measures our degree of belief in the hypothesis that the unknown parameter's value is actually equal to little theta. Step 2. Apply Bayes' rule to find the posterior distribution of the random variable theta conditional on the observed data. This step is called the Bayes update step. Step 3. Once we know the posterior distribution, we could plot a histogram of it or report it in whatever other way we like. So, what do these steps look like in practice? Well, we've seen two ways to do all this. That's been the whole story of this week's videos. Here's a recap of the computational approach, a recap of what we learnt in section 5.2. For step 1, the prior, we'll take a sample of values from the big theta random variable. For step 2, we compute weights, one for each sampled theta value. We let weight wi be the likelihood of the whole data set conditional on the parameter taking value theta subscript I, and then we rescale all the weights to sum to 1. For step 3, we can use these weights to estimate posterior probabilities. There's a formula here on the slide, but we saw in section 5.2 a very simple one-liner code snippet for plotting a histogram of the posterior distribution using these weights, and that's all we're going to be using in this video. In the next video, we'll think about cleverer ways to report the posterior distribution. Alternatively, we can do all of this mathematically using the method from section 4.2. Step 1, write out the prior likelihood function. Step 2, write out the posterior likelihood function using Bayes' rule and find the constant kappa that we need to make this be a valid density function. Step 3, whatever we want to report, we should derive from the posterior likelihood function. For example, we could simply plot this PDF. That's the theory. Okay, let's use it. Let's work through some examples. I have a coin which might be biased blah blah blah. Using the prior distribution blah, find the posterior distribution. Here are the standard steps for solving these problems computationally. The starting point is a probability model for the data. The question doesn't tell us explicitly, but we've seen enough coin toss examples by now to write down a sensible model. Let's say the random variable big X is binomial with parameters n and theta. We know little n is 12, and we don't know theta. Next step, take a sample of theta values from the prior. The question tells us to use a uniform prior, so that's what we're sampling from. Next step, compute the weights. The weight is just the likelihood function for the data set, and we write that out at the top. I didn't bother computing the binomial coefficient at the front because we're going to rescale the weights to make them sum to 1 anyway, and so any non-theta terms will just cancel out. Finally, report whatever we like. For example, we could plot a histogram of the posterior distribution, which we can do very easily with matplotlib using the weights equals w option. So that's all there is to the computational approach. Let's run through this question again, but this time we're going to do it mathematically. Our probability model for the data is exactly the same as before. It's just the next 3 steps that are different. Step 1, write out the prior likelihood function. The question tells us that the prior distribution is uniform in the range 0 to 1, so the prior likelihood function is constant, equal to 1. Step 2, use Bayes' rule to find the posterior likelihood. The answer is some constant kappa times the prior likelihood for theta times the likelihood for the data x, which we wrote out above. We don't need to carry around the non-theta factors, we might as well just amalgamate them all into the constant kappa. And then we could use integration to find kappa, or if we're cleverer, we'll spot that this looks like a standard density function that we know and love, and after a quick trip to Wikipedia, we can identify the posterior distribution as a beta with parameters x plus 1 and n minus x plus 1. Finally, report the posterior however we like. We could just stop here and say, it's a beta random variable, or we could plot the likelihood function. It's a standard random variable, and so we can find its PDF in the standard library, scipy.stats. Good. This is basically all there is to Bayesian inference. But I'm going to go through another example just to highlight some issues that might be confusing the first time you see them. Here's the example. Pause the video and have a read. The data model here, the distribution for x, has two unknown parameters a and b, and as we're being Bayesians here, we're going to treat all the unknown parameters as random variables. The question actually tells us precisely what distribution to use for the unknown parameters a and b. But now, the bit that might be confusing, the question asks us, find the posterior distribution for b. You might have alarm bells going off now. Okay, I want to find the posterior for b, so I should write out the prior for b. But then, where does a come into the picture? Hold tight, stay focused, and just follow the steps exactly as we put them up before. Let's do the computational approach first. First, we have to write out our probability model. What I've written on the left are the general guidelines, but we have to translate them to our setting. First question, what is x? X should always be the entirety of the data set that we are given. It's a sin to waste data when we could be using it to learn from. So here, x denotes the entire sample x1 up to xn. And what's theta? Theta should be the entirety of all the unknown parameters. There are two unknown parameters in this question, a and b, so theta stands in for the pair a, b. Okay, so now let's write out the probability model here, the likelihood of x. We've looked at this sort of probability model several times already in the course. Here we have a sample x1 up to xn. First I'd write out the likelihood function for a single observation, and because the boundaries a and a plus b are what we want to reason about, I've written out the likelihood in this indicator function notation. That's a trick we used right at the beginning of the course. And then the likelihood for a sample x1 up to xn is just the product of likelihoods for each individual data point, assuming independence. The question doesn't actually tell us that they're independent, but the general convention is to assume the question means independence unless it explicitly tells us otherwise. Still, we're making an assumption, so I had better write down the assumption we're making. Finally, just a little bit of algebra to tidy up. I'm going to want to evaluate this likelihood function for every single one of my sample theta parameters, so I might as well write it in a way that lends itself to a slightly faster implementation. Here, the only way that I can get 1 out of this likelihood formula is if all of the xi lie between a and a plus b, or in other words, if the min is above a and the max is below a plus b. So that gives us the simplified expression here. Okay, so now we have the probability model all sorted out. This is a good time for you to pause the video and work through steps 1 to 3 yourself. Can you write the code to answer this question? It would be a good exercise to actually implement this code yourself to make sure there aren't any gotchas hiding here. It's quite easy for gotchas to hide if all you're doing is writing down pseudocode with pen and paper. When you're ready, press play. Step 1 seems easy. Take a sample θ1 up to θn from the random variable theta. Remember, we said theta is a pair of unknowns, theta equals a, b. So this instruction is telling us to take a sample of AB pairs. The question tells us what distribution to use as the prior for A and what distribution to use as the prior for B, but it doesn't actually say anything about AB pairs. So, as per our general convention, we'll assume the question implies that A and B are independent under the prior distribution. Because they're independent, we can just generate a whole load of A samples and a whole load of B samples. Logically, we should really zip up these two lists to create a single list consisting of AB samples. I won't actually do that because in the code that follows I just have to unzip that list of pairs, but morally you should pretend we've zipped up these two lists into a list of pairs. Next step is to compute weights by evaluating the data likelihood function. There's nothing to this really, it's just a matter of turning our likelihood function into code and then evaluating it for each one of our A/B samples. This code uses NumPy vectorized operations, and you should look at it very closely to make sure that you can see why W is a vector. The final step is to draw whatever conclusions we want using our weighted samples. This is where the subtlety about multiple unknowns comes in. The question asked us, find the posterior distribution of B, but what we've actually computed with our weights is the posterior distribution of the pair AB. So all I'm going to do in this code here is ignore the A values. If you have a function that returns a pair of random numbers and you only want to use one of them, you simply ignore the other. That's exactly what I'm doing here, ignoring the A part of the AB pair and just plotting the B part. In my code, this subtlety is so subtle that it probably either seems completely obvious or completely mystifying. Let's switch over now to the maths way of answering the question, and then we'll see that it's actually a solid chunk of work. Okay, the maths approach. Whether we're giving the computational answer or a maths answer, we start in exactly the same way with a likelihood function for the data little x. Now, here are the steps to follow. First step, write down the prior likelihood for theta, i.e. for the pair AB. The likelihood of a pair of random variables is just the product of the likelihood for each of them, assuming independence, which we shall do because the question doesn't tell us otherwise. And I just looked up Wikipedia to find the PDF for the distribution named here in the question, the exponential distribution. Next, find the posterior likelihood using Bayes' rule. We'll just copy out the terms here, kappa times the prior likelihood of AB times the data likelihood of the dataset x1 up to xn. And the constant kappa is whatever is needed to make the function integrate to 1 when we integrate over all A and B. But I don't recognize this as any sort of standard likelihood function, so I can't write out a nice easy solution for kappa. Mathematica might be able to help us here, but probably not. Final step, report on the posterior. The question asked us, find the posterior distribution for B, but what we just calculated above is the posterior likelihood of the pair A, B. So, to get the likelihood for just B on its own, we have to integrate out A. This is called finding the marginal for B, or sometimes it's called marginalizing out A, or sometimes it's just called applying the sum rule. Anyway, this is another intractable integral. You can see now why the computational approach is so handy. We can actually come up with answers rather than just throwing up our hands and saying, I can't solve this integral. Okay, that's all there is to Bayesian inference. Let me just highlight the important points about what we've been doing. First, whenever we use Bayes' rule, we should apply it to all the parameters in the question simultaneously. We should start by writing out a joint prior distribution for all of the unknown parameters, and then we will get a joint posterior distribution for all of them. It might help keep your thinking straight if you explicitly write, I shall let theta be a tuple consisting of the unknown parameters and then apply Bayes' rule to theta. It's only right at the end, after applying Bayes' rule, that we decide what to do with the joint distribution. If the question only asks us about one of them, we just marginalize out the ones that we want to ignore. Technically, we don't actually have to include all the unknowns, but trust me on this, and for the first year of doing Bayesian calculations, always write out all the unknowns. After a year, you'll understand it all, and you'll know when it's safe to take shortcuts. The next tip is something that we haven't talked about. When you're answering these questions computationally, and you need to work out the likelihood of the data, you can run into underflow problems. Let's say we've got 1 million data points, n equals 1 million. Then the likelihood of the data is the product of 1 million terms, often each of them fairly small, and so the likelihood of the full data set is minuscule. And if you just compute it naively, you'll run out of floating point accuracy. You need to be clever how you actually compute it, bearing in mind that in the end you'll be rescaling the weights anyway, and the printed notes suggest how you can do this safely in your code. Okay, so that's Bayesian calculation. All Bayesian questions are exactly the same. Write down the prior, find the posterior. What's actually the hardest part of Bayesian machine learning is working out how to frame our question as a Bayes rule type problem in the first place. In other words, how do we turn a real-world problem into a question about random variables? Here's the question we opened with, the question about how confident we should be in our estimate of global warming. And this was the crucial step, the step where we said, I know what, I'll treat my unknowns as random variables. Once we made that leap, the idea of parameter uncertainty pretty much drops out automatically. But sometimes it's rather tricky to actually see what the unknown parameter is that a question needs us to spot. Let's work through one last example to illustrate. Here's a question about classification. I'll give you a moment to read it to yourself. In the examples we've looked at so far in this video, the question has clearly told us, here is an unknown parameter, and so we knew we had to treat it as a random variable and find its posterior distribution. But in this question, where are the parameters? I can see lambda L and lambda F. Are those the parameters we're reasoning about? No, the question tells us values for those parameters. They're not unknown. No, what we have to do is look at the question and work out, what are we uncertain about? This question asks us, is this claim for X likely to be fraudulent? So that's what we're uncertain about, whether or not this claim is fraudulent. So the next question is, how do we represent our uncertainty? What do you think? Pause the video and see if you can work out what we need to do here. How can we think of this uncertainty as an unknown parameter? Once we manage that, how do we go about answering the rest of the question? Stop and think, and when you're ready, press play. The Bayesian answer is always, we represent uncertainty by means of a random variable. Let's invent a random variable big theta, whose possible values represent the possible resolutions of our uncertainty. Let's say theta takes values either L or F. It takes value L if the claim is legitimate, F if it's fraudulent. Next, the Bayesian asks themselves, what's the prior on this uncertainty? The question generously gives us a hint by using the word prior. It tells us, in my prior experience, 99% of claims I've seen are legitimate. We can use this as our prior. We'll say that the prior distribution on theta is theta equals L with probability 99%, theta equals F with probability 1%. Okay, now we've got all the random variables properly defined. The rest of the question is just plain sailing. In fact, we've already answered exactly this type of question before in section 4.2, so I'm not going to go over it again. All I wanted to do with this example is to give some guidance about how to look at a real-world problem and think to yourself, aha, this is what I should treat as random. I think that's the real tricky thing about Bayesian questions. The rest is just the standard three-step procedure, exactly the same for every single Bayesian question. In the notes, you can read about how Bayesians can treat even a model choice question, should I believe model A or model B, as a question about an unknown parameter. Here, model A says there is global warming, model B says there isn't, so it's obviously very useful to be able to say how much evidence we need to reject model B. But Bayesian model comparison is off syllabus, so I won't go into it in these videos. Okay, so we've learned how to formulate a question as a Bayesian maths problem, and we've seen how to solve it both computationally and mathematically. There's only one small piece left. What do we do with the posterior distribution we've found? In the examples in this video, all I've done is say, hey, we could plot a histogram of the posterior distribution. In practice, there are a couple of standard readouts to give, and that's what we're going to look at in the next video.